Hi everyone, you're welcome to this tutorial. Today we're going to treat thermodynamics in electrochemistry, and we're focusing on the Nernst equation. Nernst is a German chemist or physicist that will work on relationship between the electric potential of a cell and the activity coefficient or particles in the cell. He derived his equation based on the third law of thermodynamics. So here we go. In determining Nernst equation, the first step we take is to know that delta G is equal to negative NFE. So delta G implies the change in Gibbs free energy. Gibbs energy, which is the energy required to do work in a chemical system. N is the number of moles of electron transferred in a redox reaction. F is the Faraday constant, and E is the cell potential. Also, we should also know that delta G, our standard state, given as minus number of moles times Faraday constant times the cell potential as standard state. What do you mean by standard state? That is when the cell potential is measured at 25 degrees Celsius, which is equivalent to 298 Kelvin, and pressure of 1 atmosphere. So when we measure the standard cell potential or the cell potential at this condition, or we measure the change in Gibbs energy at this condition, so we now have the standard change in Gibbs energy and the standard cell potential. Then the relationship between the Gibbs free energy and the standard value is given by delta G equal to delta G as standard state plus RT ln or natural log of Q. So this is the change in free energy at any temperature. This is the change in Gibbs free energy at 25 degrees centigrade, that's standard value. This R is called the gas constant. Then T, temperature in Kelvin, and Q is natural log. Then Q is called activity coefficient. Then we're going to substitute these values into this equation. We now have negative NFE, that is this, coming into this place, equal to negative NFE as standard state, that is this one replacing that, plus RT ln Q. Dividing both sides by negative NF, so this will cancel. We have E equal to E as standard, that is the potential equal to the temperature as standard state, plus, minus now, RT NF ln Q. So we look at the work we have done. The Gibbs energy related to the electric potential of this formula. Then our standard state will now put 0 or theta on G and also on E. Then substituting this one with this value, we'll have this. Substituting this one with this value, we'll have that. And then plus, I'm going to divide both sides by NF, we'll come to this equation. We are still working on this. Then having done that, we'll continue from here. So we know that the natural law related to log to base 10 with this equation, natural log of a number given by 2.303 log of the same number. We now bring relationship into this equation. We now have E, the potential standard state, minus 2.303 log 2.303 RT over NF log Q, replacing natural log S with this value in this equation. Then having done that, we know that the gas constant R is 8.314 joule per mole per Kelvin, and the Faraday constant is 96500 coulombs. We now bring in these values into this equation. We now have E equal to E at standard state minus 2.303 times 8.314 times. Yes, standard temperature should be 25 degrees or in Kelvin, 298 Kelvin times 298 all over N times Faraday constant, then log of the activity coefficient. If we solve all these, we now have E equal to E0 standard state minus, if we evaluate all these, we're going to have 0.0592 approximately over N log Q. So this is the Gibbs equation. The Gibbs equation. What's the name again? The Nernst equation. So which is derived from the law of thermodynamics. Then what does this Q represent? As we said, the Q represents that coefficient. As we have an equation A, B, giving us C plus D. Where small letter A and B are the small letter A, B, small c, and small d are the stoichiometric number of moles. Capital A and capital B are the reactants. Capital C and capital D are the products. So how do we write that big coefficient? So that is nothing but the ratio of the concentration of the product raised to each number of moles divided by that of the reactants also raised to their stoichiometric number of moles. That's what we call the activity coefficient of a reaction. So, having done that, then the question is this. If this is the Nernst equation, E equal to E at standard state minus 0.0592 and log of the activity coefficient. Then what happens when we have dynamic equilibrium? When a reaction attains dynamic equilibrium, that is when the rate of forward reaction is equal to the rate of reverse reaction. At dynamic equilibrium, the value of the rate of potential of the cell becomes equal to 0. And then the activity coefficient Q becomes equal to K, where K is called the equilibrium constant. So, replacing this in this equation, or substituting E with 0 equal to E as standard state minus 0.0592 over N log K at equilibrium. So carrying over like terms to this side, we have E0 becomes equal to 0.0592 over N log K. If I make log K the formula, log K, where K is the equilibrium constant, becomes N E raised to the power 0 all over 0.0592. So with this, we can evaluate the equilibrium constant when the reaction has attained dynamic equilibrium. Okay, so what have we learned today? We have been able to derive the Nernst equation, given that the rate potential of a cell is equal to the rate potential, so the cell potential equal to the cell potential at standard state or at ordinary state. The cell potential at ordinary state equal to the cell potential at standard state minus 0.0592 over number of moles of electron transferred log Q is the Nernst equation. Then at equilibrium we have log K equal to N, then the cell potential as standard state all over 0.592. Equilibrium goes when the cell potential at ordinary temperature went 0 and and then the atomic coefficient now becomes equal to K, which is the equilibrium constant. Now we're going to take examples to see how we can illustrate the Nernst equation. The first question we have here says, calculate the equilibrium constant. Calculate the single electrode potential for copper metal in contact with 0.10 molar copper 2 ion solution. And then we're given that the rate potential for copper to be equal to 0.34 volts. So how to tackle this problem? Looking at this problem on the board, this is a problem involving a single electrode. So the first thing we have to do is to write the reaction occurring at the electrode. When a metal is in contact with its own ion, the ion in solution becomes reduced. And we know in chemistry, reduction is electron gain. The copper 2 ion will reduce by gain electron from the copper. So plus getting 2 electrons, giving you copper solid. So having done that, we can now write the Q as the coefficient. Q now becomes the product concentration. Product is copper all over reactant concentration, which is copper 2 ion. And in chemistry, when a substance is in solid state or liquid state, solid or liquid state, we take its concentration as unit, as 1. So this copper is in solid state, we take the concentration as 1 all over copper 2 ion. So that's why this one is now replaced as with 1. Then using the next equation to solve this, we now have, whatever the formula I have up there, we now have E, working for the electric potential, E, yeah, for cell potential, that will now give us the standard cell potential, which is 0.34 volts minus 0.0592. How many electrons were transferred in resin copper was used again, there is 2 moles of electron. Now it's all over 2. Then log of 1 over C, that is the copper 2 ion quantity is 0.10 here. So replacing some two values, the potential as standard state for copper is given to you here, 0.34. Then 0.0592 in the formula all over, and number of moles of electron transferred. Then using that coefficient, bring it here, bring it in. Then the copper concentration is only 0.1. So solving this, we're going to arrive at E equal to 0.34 volts minus 0.0296 log of 10 power minus, this is going to give us log 10. Yeah. When we solve, we now have E equal to 0.34 volts minus log 10 is 1, 0.0296 volts to give us the cell potential of copper, and that will give us definitely 0.31 volts, which is the answer. We'll take a second problem on this. The second question says, calculate the equilibrium constant K for the reaction below and the equilibrium concentration of ion 2 and cadmium ion. You have this equation Fe solid plus cadmium 2 ion aqueous, giving us ion 2 aqueous plus cadmium solid. We are given the cell potential standard state for this reaction as plus 0.04 volts. So let us tackle this problem. To solve this problem, first of all, there are two questions in one here. The first say we should find the value of K at equilibrium. Then the second one is we should look for the concentration of the substances at equilibrium. So let's start by finding the value of K at equilibrium. I will know from the next equation at equilibrium the cell potential at ordinary temperature becomes 0. And then our Q becomes equal to K. Replacing these values here, I have 0 equal to E0 minus 0.0592 over N log K. So we try to swap. We now have E0 equal to 0.0592 over N log K. So making log K the subject, log K becomes equal to N times standard electric potential all over 0.0592. So this is the equation we need to find our equilibrium constant. So now what we need, I have to clean the board and use the upper side. So log K, that is equal to N times standard cell potential all over 0.0592. We look at this equation now. We are given the standard potential of the cell, which is 0.04. Now log K, substituting our values, and number of moles of electron transfer is 2 in this reaction. Then the potential E, the standard potential is 0.04 all over 0.0592. So finding log K or solving for log K, we'll have to use a calculator to press this and get the answer. So we'll have log K will give us 1.4. So taking the log inverse. So K now becomes log inverse of 1.4, that will give us 20. So this is the equilibrium constant for this equation we are asked to solve. Then we also asked to find the equilibrium concentration of ion 2 and cadmium 2 ion. To solve that, what we'll do? What we'll do is we'll now write the equilibrium expression K begin as the product concentration ion 2 all over the reactant concentration cadmium 2 ion, and that is equivalent to 20, which we calculated just a few minutes ago. Then we know that the question is, why is cadmium solid and ion solid state not appearing here? As I said initially, when elements are in their solid state, we take their concentration as unit as 1, and they will not appear in the equilibrium constant or in the activity coefficient expression. So having done that, we now say let X represent the concentration of cadmium converted to product. So let S represent the cadmium product. Then concentration of cadmium remaining at time t will now become 1 minus X. While concentration of ion 2 formed or produced at time t will now be equal to 1 plus S. So if S represents the amount of cadmium that is transferred to the product at equilibrium, so the same S also represents the amount of ion 2 that is produced at equilibrium at a particular time. So the of cadmium remaining will now be 1 minus the amount of S that is removed, while the of ion 2 remaining at the same time will now be 1 plus S. Now how come the 1? We know that at standard state or at equilibrium, the concentration of the substances remain of the substance in the equation be 1 mole per dm cube each. So we now replace these values in this expression. That's a 1 plus S for iron all over 1 minus S for cadmium equal to 20, which is the every constant expression. We now cross multiply 20 into 1 minus S equal to 1 plus S, since what we have is 1 denominator. We now have 20 minus 20S equal to 1 plus S. Solving, we now have, taking like terms, 20 minus 1 equal to S, 20 minus 1 equal to S plus 20S. So solving this, we arrive at 19 equal to 21S. Making L the subject, L becomes 19 over 21. So when we divide this, we are going to have 0.9 mole per dm cube. So this represents the amount of cadmium converted to the product and also the amount of ion 2 produced. So the amount of chromium converted to cadmium, converted to product, and the amount of ion 2, the gain in cadmium loses 0.9 mole per dm cube, while ion 2 gains 0.9 mole per dm cube. So the concept of cadmium now becomes from here, remaining now be 1 minus S, which is 1 minus 0.9, which will give us 0.1 mole per dm cube. Then for ion 2, we now have 1 plus S, which will be 1 plus 0.9, giving us 1.9 mole per dm cube at equilibrium. So we take our final question for today on Nernst equation. Question says, calculate the EMF of the cell in the reaction below. Magnesium solid plus silver ion aqueous, magnesium 2 plus aqueous plus 2 silver solid, and we're given the concentration of magnesium to be equal to 0.130 mole per dm cube, and that of silver ion to be equal to 1.0 mole per dm cube. Okay, and we're also given the electropotential of silver ion going to silver as minus 0.80 volts. We're also given the potential of magnesium ion going to magnesium as 2.37 volts. Okay, having done that, we'll now look at this, how to evaluate this problem. So we're looking for the EMF. EMF sets as cell potential. Anyway. So having done this, we have to establish we are given the electropotential of the two half cells. So with this, we first of all calculate the cell potential of the cell at standard state. how to go about that? We now say the cell potential giving us the potential of the cathode minus the potential of the anode. So out of these two half cells, we want to identify the one that will form the cathodic half cell. When you have two metals represented with the potential, the one that will represent the cathode is the one or the least reactive metal. The least reactive metal here is silver. How do you know that silver is least reactive? Visit your electrical series that says so this is the activity series or electrical series that shows the reactivity of common metals. We can just say how many mnemonics to remember it. That is, somebody can just say, please stop calling me a zebra. Instead, please stop calling me a zebra. Instead, tell Laura how copper helps strengthening. Good. You kind of need to remember it, to know it. Please stop calling me a zebra. Instead, tell Laura how copper helps strengthening. Good. We have P here represent the element with potassium by using K for the Latin derivative. Then stop, S therefore sodium, Na for the Latin name, calling, Ca calcium, M therefore magnesium, A for aluminium, zebra, Z therefore zinc. Instead, I there is iron, ferrium, that iron. Then tin, T is for tin, stanium. Laura, L for lead, Pb plumbium. Then how, H for hydrogen, C for copper, helps. Then silver, that is argentum, silver. Then gold, arium. So this is at this area. So look at this silver position is here, and look at magnetic position. That means silver is less reactive. The metal that is less reactive forms the cathodic half cell. So this represents the cathode. We now have minus 0.80 volts. Then this represents the anode. That is a magnesium. The is a 2.34. So the error in the sign that should minus here instead. So minus, then minus 2.37. So that is, the error is correct. This is positive, this is negative. So solving this, we have 0.80 plus 2.37. Using our calculator, we can now get our electropotential for the two half cells to be equal to 3.17 volts. So this is the standard cell potential for the cell when the two of them are coupled together. 3.17. Having gotten that, we can now go back to our next equation, applying E equal to E0 minus 0.592 over N log Q. Then how do we get our Q? From here, Q is the activity coefficient, which is the concentration of the product. The product there is magnesium 2 ion. Silver will not appear because it's solid. All over, the reactant is silver 1 ion raised to power 2 because of 2 moles of silver in front. So that is it. Why I have 2 here. Magnesium will not appear because it's solid. So because of solids are unit 1, so we ignore them in this activity coefficient expression. So having done that, we now make our substitution and solve. Finally, we now have E equal to, these have been calculated before as 3.17 minus 0.592. 2 moles we are transferred of electrons. Then log of as we say, magnesium ion concentration up, then silver ion concentration raised power 2. So when we solve again, continue 3.17 equal to, minus, that gives you 0.296 log. Put the value of magnesium ion concentration here is given to us as 0.130, while that of silver is given to us as 1 times power minus 4 squared. So solving this with our calculator, we can evaluate this under log. We now have our final answer as 2.96 volts when you solve this. So this is the electric potential or the EMF of the cell which is described above. So EMF refers to the potential difference between the electrodes in a cell when the cell is operating in an open circuit. So having done that, we are seeing the next equation and how it's applied in thermodynamics. Please subscribe to the channel, like, make your comments for us to improve better. Also, need to remind you that we're also on Facebook. We're on Facebook. You can get us on Facebook with the same channel name, Best Science Brain. So check us up, Best Science Brain on Facebook. The words are joined together. So go to Facebook, search Best Science Brain and follow us on Facebook. See you next time. Thank you.